Valentin Boyanov from Instituto Técnico in Lisbon. And Valentin will talk about the evolution of black hole interiors in classical gravity. Feel free to ask questions during the talk, and there will be also more time at the end. And Valentin, thanks a lot for being here, and you have the floor.
Thank you. Thank you for the invitation to give the seminar. Thank you all for coming today. So yes, as Jordan said, I'll be telling you about my work on the evolution of the interior of black holes, both in classical and semi-classical gravity. This is a work I began during my PhD under the supervision of Carlos Barceló, Raúl Carvalho Rubio, and Luis Garay, and that I've continued in my postdoc in CENTRA with Dave Hilditch, Artur Semial, Vitor Cardoso, and Jen Nong. Well, to begin with, let's go back over what black hole formation is. So usually when one thinks of the non-uniform black hole, one thinks of a collapsing distribution of matter that at some point becomes dense enough that trap region forms around it, and then it continues collapsing inside trap region, following the light comes there, and at some point infinite density is reached and singularity is formed. That's the usual picture. But if you actually consider a more generic scenario in which the black hole, say, has angular momentum or well, also in general, even if it doesn't have angular momentum, usually what happens is that horizons tend to form in pairs somewhere inside the matter distribution. And you have the outer horizon, which classically can expand outwards, so it's more matter accreted. But you also have an inner apparent horizon, which is the inner boundary of where outgoing light rays have negative expansion. So they have negative expansion inside the trap region, but they again have positive expansion below it. And the inner horizon, which marks its boundary, either goes to the origin if, let's say, a Schwarzschild black hole forms, or it tends to hover at a finite radius if the black hole has electric charge or angular momentum. Now, what happens with this picture is that inner horizons, long-lived inner horizons, actually tend to be unstable. And to see that, you can first notice that if we look at the behavior of geodesics, which approach this inner horizon, in the vicinity of the horizon, there is a discrepancy between the time that passes for the outside universe and the proper time of observers or defined parameter of geodesics that approach this horizon. And this discrepancy becomes so large that an infinite time can pass for the outside universe, while only a finite time passes for these observers. And the relation in particular is the same as the defined parameter of the geodesics. Then it has this relation with the advanced time v of the exterior, where kappa I is the surface gravity of the inner horizon, absolute value. And this leads to the formation of a Cauchy horizon, beyond which these geodesics can be extended, and space-time itself can be extended. And in a causal diagram, it looks something like this. So from the previous picture, the outer horizon would be this part here, and the inner horizon would be this branch here. And the Cauchy horizon that forms at v tending to infinity would be this going right here. And well, this is slightly different from, so I put it on top of a diagram of the maximal extension, but keep in mind that in the maximal extension, this branch here is also part of the Cauchy horizon, but for geometries of dynamical formation, this is not the Cauchy horizon, it's just the dynamical inner horizon. And well, the instability of the inner horizon can be seen by the fact that it tends to form a Cauchy horizon, and perturbations tend to be blue shifted when one approaches the Cauchy Cauchy horizon. Particularly if you think about sending some signals into the black hole from the external universe, let's say that you space them equally in time, then for an observer that's outside the black hole, nothing strange will happen. They just send pulses. But for an observer that approaches the Cauchy horizon, those pulses tend to get bunched together because, well, an infinite time passes here, only a finite time passes here. And even if the energy of these pulses increases such that you don't throw an infinite amount of energy into the black hole, let's say that this energy that you throw in is the cases in inverse polynomials, such as the tail of the price law, perturbations, generic perturbations outside black holes, or as a decaying exponential with cosmological cases with a coefficient that corresponds to the surface gravity of the cosmological horizon. As long as this decay is slower than this exponential here with the surface gravity of the inner horizon, which happens also for cosmological cases when the cosmological constant is very small, then you get an infinite density at the Cauchy horizon. So this bunching together of pulses at infinity leads to an infinite accumulation of energy there. And, well, this is, let's say, the source of the mass inflation stability, but in practice, to see it, you also need to consider outgoing fluxes. So the full nonlinear effect is only present when you consider both ingoing and outgoing perturbations. And the outgoing ones you can think of as backscattered waves from the infall generic perturbations. And the simplest way to get an intuition for what happens during mass inflation in the interior of the black hole is with a model that can be constructed simply with a series of thin shells. So the outgoing backscattered flux is, for it, it's enough to put a single outgoing null shell inside the trapped region. And for the ingoing flux, we can model it with a series of ingoing shells of decreasing mass. And, well, we consider that, so we start with a black hole that has this one here, so standard vacuum-like form, and time coordinates, where the redshift function has two zeros, one corresponding to the outer horizon, one corresponding to the inner horizon. And with this construction, we can obtain the full nonlinear solution just from the junction conditions. So just from specifying the masses of each shell and the junction conditions at the intersection points between the shells, which is from here between the redshift functions in each region. I should say the metric can be written in this form in all regions, on all sides of the intersection points, but in different coordinates. So in some coordinates it's like this, but say the v coordinate of the exterior and of the interior of the outgoing shell will be different. We'll see that later. So with these junction conditions, what happens is that we can see that the redshift function f on the interior in the future of the intersection point between the shells acquires exponential growth, which can be related to a growth in Wisner sharpness, which is inside this function. And the exponential goes with the time that the outgoing shell decided to approach the inner horizon between one intersection and the next. And it has some prefactors, so this exponential need not accumulate over time if the prefactors keep compensated. And particularly the prefactor that's most important is this difference between the inner horizon positions in regions C and B. So the inner horizon as seen from the outside, so from the extension of the exterior geometry, this difference between regions C and D, if this difference is any larger than this exponential here, then this pre-factor doesn't compensate the exponential, and you get overall an average exponential growth of the redshift function corresponding with the Mizzen-Sharp mass. It is interesting to note that while this condition is true for, let's say, the Rasen-Roentgen black hole and the Kerr black hole, because the relation between the horizon position and the mass is polynomial, you can, in principle, devise some modified gravity regular black hole model in which this condition isn't satisfied and in which this nonlinear mass inflation effect would not happen. But if the condition is satisfied, then, as I said, you get an exponential growth in the sharp mass in the region below the outgoing shell. So I'm not saying that the mass is seen from the outside, the mass of the black hole grows exponentially. The mass from the outside only grows in as much as you add mass from these incoming shells. But the nonlinear effect happens below the outgoing shell. So in this interior region, the quasi-local mass there and the curvature scalars tend to increase exponentially. And that's what happens to the sharp region. All the inner apparent horizon actually tends to go as it's decaying exponential toward the origin. And the metric, if written in the Finkelstein coordinates of the exterior region, acquires the metric in the interior, and the mass inflation region acquires this form, where this factor A comes from the change of coordinates between the exterior and the interior regions. And it has this decaying exponential form. And we call it the freezing function because its effect on the geodesics inside the trapped region is such that it freezes outgoing geodesics and an approach toward different finite radii asymptotically. So usually outgoing light rays inside the trapped region will tend to fall inwards. But because of this function, they sort of get frozen and approach toward the finite radius instead, somewhere just in the middle of the trapped region. And you also get some other light rays which stick around the inner horizon and approach the origin as the inner horizon does. And this leads to the presence of two types of singularities asymptotically. There's a strong curvature singularity, which corresponds to all of the, in which all of the light rays that stay close to the horizon fall into. And then there's a weak no singularity, which the light rays that get frozen inside the trapped region approach. And the strong singularity can be, well, in the shell model, it actually has a no component, but in other linear models, which you have, let's say, a scalar field instead of shells, it's expected that you have a space-like, well, that this singularity be space-like rather than no. But there's no rigorous proof, I should say. And also, I should say that a strong singularity refers to the standard Schwarzschild-like singularity, where well, curvature scalars diverge and things that fall into it get destroyed. Whereas a weak singularity actually means that you still get divergence in curvature, but an object that passes through the singularity, its overall integrated deformation, so the integration of the geodesic deviation equation remains finite. So while you still have a divergence in the curvature scalars, the metric actually ends up being continuously extendable. So in a sense, the Cauchy horizon is not fully destroyed because it can still be feasibly crossed by observers. But this is at the classical level. So if there are any questions about the classical picture, that would be a good point.
We just found more about these strong null versus space-like singularity outcome. What's known about it and what's stated?
Well, as far as I know, there are a lot of studies about the Cauchy horizon itself. There's been a lot of focus on the weak singularity because, well, originally it was expected that maybe the mass inflation singularity would preserve strong cosmic censorship in preventing an extension to another universe. But as for the strong singularity region, there are some numerical studies that suggest that, well, its formation is approached, and it's known that at the end of the radial coordinate at the weak singularity goes between the initial R minus and 0, and when it's 0, it meets the strong singularity. But the evidence for the causal nature of the strong singularity itself is only numerical, and so it's not proven to be either one or the other. In the shell model, it's no, but it's also true that the shell model is not fully generic because I only put a single outgoing shell, which leads to a single exponential amplification of the mass and the curvature in the interior region. And if you put multiple shells, multiple outgoing shells, you can actually get a further exponential amplification of the effects. So you can get stuff like the exponential of an exponential. And so it's not clear in the case in which you have a continuous field how that would average out, let's say. So it's not necessarily the average result of the shell model is not necessarily the same as that of a continuous field case for this interior region. So basically, it's not known yet, as far as I know.
Maybe also I have one, but it's more about the weak singularity. What would happen, say, if I don't know, if an observer or a lecturer or something crosses that? It says the metric can be extended, but still there are some singularities in the curvature. So
yeah,
just to get a better, say, physical feeling of what it would mean.
Well, yeah, what happens is basically that you get, you have a curvature singularity, but the integral of the geodesic deviation equation remains finite, which means that an object that's, you can think of like 2 points of an object following two geodesics that are next to each other, ignoring the internal forces that keep the objects together, then its deformation will be finite when it crosses the singularity. It's not like the Schwarzschild singularity where everything gets compressed to a point. Here you get some abrupt deformation when you cross it, but still finite. And so yeah, that's the physical picture, and mathematically that translates to the metric being C0.
I was just wondering if there was something that could be measured, for instance, so that you could say, okay, at that moment, say I've passed the singularity.
Yeah, I think an abrupt deformation, but still a finite one of the object. And again, this is still at the classical level. When you add quantum effects, then things get more interesting. Any other questions? Let's move on to the semi-classical part. So, semi-classical gravity is a theory where typically one considers, well, one takes the Einstein equations, and usually you can keep the effectively classical source, so the effectively classical stress energy tensor, which generates the bulk of the dynamics, say our stars and planets and collapsing matter that form black holes. But you add on top of it contribution from matter that doesn't behave classically, effectively. And this contribution is the renormalized stress energy tensor, which is the renormalized vacuum expectation value of an operator constructed from quantum fields which live on the space-time. And since it's the vacuum expectation value, it still retains its quantum behavior. And once you calculate this quantum field and renormalize it, it ends up being a function of the geometry. And so these equations essentially behave like a modified theory of gravity. But, well, it's more like a modified theory of gravity than adding an exotic source, because this term here has higher derivatives of the metric, so it modifies the principal part of the equations. And also, in general, it's suppressed by constants, so in practice, it's the classical part that generates the bulk of the background dynamics, and the renormalized stress energy tensor only acts as a small perturbation. But in some particular geometries, you can have significant semi-classical corrections, either because they accumulate over time or because some nonlinear amplification. And in particular, it's been found that you can have significant corrections around trapped regions, and this relates to the way, particularly around horizons, the way light rays and consequently modes of the quantum field behave, the, let's say, peeling of light rays off of the outer horizon and the accumulation around the inner horizon. Now, calculating the normalized stress energy tensor is a very challenging task, and ideally we would want to do it for all of the fields of the standard model. So quantizing the full interacting theory in an arbitrary curve background, but well, with current techniques that's not really feasible. So what we typically resort to is performing calculations with test fields such as the massless scalar. In this case, I'll look at one that's minimally coupled to gravity. But even in the test field case, calculations that are exact and four-dimensional can only be performed typically on simple static backgrounds. If we want to look at dynamical backgrounds and look at back reactions and self-consistent solutions, we have to resort to a further simplification, which in this case will be the use of the Boyanov approximation for the normalized stress energy tensor, which is based on dimensional reduction. So we basically quantize a field on a 1+1 dimensional geometry, which corresponds to the radial temporal sector of the 3+1 spherically symmetric geometry. And then we define a four-dimensional tensor related to the two-dimensional normalized stress energy tensor result. And this has been shown to capture effects like Hawking radiation, but it has a non-physical singularity at the origin, so it should be used with some caution if you want to use it on non-black hole spacetimes. But here we're more interested in the effects around horizons, where it's more applicable. There's another comment to be made about quantizing in curved spacetimes. So there's an ambiguity in defining the vacuum state and subsequent particle states in an arbitrary curved background, which comes from the lack of symmetry. So in flat spacetime, you have a preferred quantization that's related to the Lorentz symmetry of spacetime, and you have a vacuum state that's invariant under transformations, corresponding symmetry group. But in generic curved spacetimes, you don't have that. And so what's typically done to go around this ambiguity defining a preferred state is isolating the system that you're interested in studying in an asymptotically flat spacetime, and then performing Minkowski-like quantization in the asymptotic fast where spacetime is flat. And you know that the quantization works there, and then you propagate the modes of the quantum field and everything through the region of curvature in the future. This is how you define the in state, which is typically the most, let's say, physically well-motivated one to use in gravitational collapse and black hole formation scenarios. Now, there have been some works on studying the renormalized stress energy tensor around inner horizons, but they've typically been studies on maximal extensions of spacetimes that have this horizon. So particularly, they studied the values of the renormalized stress energy tensor when the inner horizon is already a Cauchy horizon and not on the inner horizon of a dynamically formed black hole. And what they find is that the renormalized stress energy tensor diverges there, and that can be related to the blue shift instability, which also leads to mass inflation, the way it affects the modes of the quantum field that live upon the spacetime, make it so that you end up with divergence in the renormalized stress energy tensor. But in these works, they don't address the question of what happens to the inner apparent horizon before it becomes a Cauchy horizon, and whether a Cauchy horizon is ever even approached, whether the formation is something that should be considered, given that it's known that within the same theory, the outer horizon evaporates very high, that the black hole actually shrinks in time, maybe in a very long time, but still finite. Whereas for a Cauchy horizon, you need an infinite time in the external universe. So there's some slight inconsistency in the whole picture if one wants to look at strictly a Cauchy horizon. But these calculations do give us some intuition about the potential late time behavior of the renormalized stress energy tensor at the inner horizon. Particularly, what they've seen is that the semi-classical source there tends to become much larger. Its divergence becomes much stronger than the divergence of the classical source, which leads to mass inflation. So the bunching of the signals of the classical perturbations that stem from the outside becomes subdominant compared to the semi-classical term. And so it's expected that on the dynamical inner horizon, therefore, at some point, the semi-classical effect may begin to dominate. And begin to study what happens to the inner horizon at finite times due to semi-classical back reaction, we can use this Boyanov approximation that I mentioned earlier and construct, to begin with, a very simple model in which we have the formation of a black hole. We take time element of the same form, same vacuum form as before, but well, to the past at some advanced time bf, we just put some patch of Minkowski spacetime for simplicity, and to the future we put the black hole spacetime, which has both an outgoing and both an outer and an inner horizon. And well, this is a simplification in terms of how typical collapse would go, even in circle symmetry. But it's essentially in order to simplify the conditions for the quantum field as it enters the black hole region, and subsequently the calculation of the renormalized stress energy tensor. So if we do this and look at the renormalized stress energy tensor in the black hole region, in the Boyanov approximation, what we find at the outer horizon is a negative ingoing flux, which depends on the surface gravity and radial positions of this horizon. And since it's negative, it leads to back reaction, which is the opposite of what one would expect classically, particularly if leads to the black hole shrinking, and this is none other than Hawking evaporation. If we take a quasi-stationary approximation and consider back reaction from this flux, we recover the Hawking evaporation result with the time scale that goes with the cube of the mass. If we do the same now at the inner horizon, we again find in this approximation a negative going flux, which depends in this case on the surface gravity of the inner horizon. Now, again, there have been some works that attempt to make arguments about back reaction in the interior of black holes, but which consider that the negative flux that falls through the outer horizon is the flux that's present in the entire interior of the black hole. But that's not how the normalized stress energy tensor works. Well, the value of the flux changes, and around the inner horizon, it depends on the characteristics of this horizon. But I should emphasize that this is within this approximation that has gone through dimensional reduction. And if we compare this result, which is valid also at the Cauchy horizon, the extension of this black hole, with calculations that have been performed on the Cauchy horizon in 3+1 dimensions, we see that they match close to the extremal limit, particularly of horizon notional black holes, but far away from extremality. The sign may change in the exact 3+1 dimensional approximation. And if we add angular momentum to the picture, so if we look at the exactly normalized stress energy tensor on the Cauchy horizon of a curved black hole, we see actually that the sign of the flux can depend on the angle as well. So here the blue regions are where the flux is negative, and the red ones is where it's positive. So it's from this, it's not entirely clear what would happen to, since this is also the Cauchy horizon and not the inner horizon at the normally formed black hole. It's not clear what the sign will be in which regions of the inner horizon. In a generic case without any symmetry, but the best we can do for now is say, okay, let's assume that we're in the limit of validity in the full approximation and see what the outcome of the semi-classical evolution will be. And in the future, we will want to explore improved analytical approximations in order to see how robust this result is. And well, as we've seen in the classical mass inflation case, the energy fluxes which cross the inner horizon tend to displace it exponentially because of nonlinearities in the evolution around this horizon. And much like the inner horizon is displaced inward exponentially in the classical case, one might expect that if the flux is negative, then the exponential displacement of the inner horizon might turn around and head outwards. And so the trapped region would then sort of not exactly evaporate, but disappear from the inside out very abruptly. And the time scale for this, if the dynamics is exponential, would be of the order of the light crossing time of the object. And well, if this were the case generically, then the dark objects that we observe in our universe would have to be some horizonless black hole mimicker, since trapped regions would have a very short lifespan. But to see if this actually happens non-linearly, what we can do is try to evolve the full semi-classical Einstein equations with the normalized stress energy tensor in the Boyanov approximation. And as an initial first simple model, we take again a black hole formed from the collapse of a shell. And in the past we have Minkowski, in the future we have a black hole region. And much like, well, if you look at the literature, there's a similar calculation done, but for a Schwarzschild background rather than Horizon Nostrum one from the 90s. We do the same, but with Horizon Nostrum background. And for now, we don't consider classical perturbations, which would lead to mass inflation on top of this picture, but we will want to do that in the future. So just for reference, this is what the equations look like. We evolve them in double node coordinates because the components of the normalized stress energy tensor have a particularly simple form in the appropriate pair of node coordinates. And well, here on the left we just have the components of the Einstein tensor, and on the right we have these three terms which come from the normalized stress energy tensor, and these two terms here which come from the classical electromagnetic tensor. And we use these two equations for evolution and top two as constraints. And we plug it into the computer and we see what the evolution looks like. So this is a contour plot of the radius in no coordinates. So this is the u coordinate, this is the v. It's oriented the same way as in a causal diagram. And here for this initial one, I've turned off the sign classical effect. And so the black hole forms from this surface onwards, from V0 onwards. And the red lines are the outer and inner horizons. And here we see that they remain static. Now, if we look at the same picture, but we turn the sign classical effect on, so we set the point length to something that's not zero, then we get the evolution of the horizons. Particularly here, I put the point length to something relatively large so that the evolution happens within our domain of evolution. But we've seen that the effect is generic. If we make the time scale smaller, then it just takes longer for the effect to kick in, but it's qualitatively the same. And what happens is that the outer horizon, as expected, begins to move inwards. Maybe not entirely clear from just this picture, but in the next one it will be. And the inner horizon begins to move outwards. And something that we didn't expect also popped up. And it was this blue line here, which actually marks the boundary of an anti-trough region. So not only do we have that both horizons approach each other, so you get sort of an evaporation from both sides. You also get an anti-trough region forming below the inner horizon, so inside the black hole. And if you, so this evolution here goes between 0 and 10 in units of the horizon radius. If we increase the time of the evolution to
so for the anti-trough, what you checked is that the expansions they were both in Boyanov, they were both.
Yes, exactly. You can see it in the contours of R. So the white lines are R equals constant lines. And you see that here the outgoing rays have increasing radius, but the ingoing ones cross in this direction. This is increasing radius. But here they turn around. So the ingoing rays could also start seeing increasing radius.
You mentioned before this behavior about the flux in the level of approximation that becomes very dominant, close to R equal to 0, right? And you said that even close to a singularity, that would be.
Right, yes, the 1 over.
Yeah, exactly.
Yes.
So you would expect sort of very strong dominating effects inwards. Perhaps not an anti-trough region,
Yes.
but
Yes, so there is part of the Boyle approximation, which is this 1 over R squared term, which can give, let's say, if you're very close to the origin relative to the time scale, then you might get some effect there, which is just an artifact of the dimensional reduction. That's possible. But So then what one check to see whether this is the case is whether this effect is robust and whether the scale of the anti-trap region changes when we make the point scale smaller. So when we make the region where it is, and also making the, well, focusing more on the region that's closer to the horizons rather than to the origin. So let's say taking initial conditions that are closer to extremality and only looking at the vicinity of the horizons and not looking at what happens to the origin and seeing if the trap region still emerges in that vicinity. And, well, first of all, if we increase our evolution time, we see the full evaporation of the trap region. So here the outer horizon is the red line, well, the lower part of the red line, and the inner horizon is the upper part of the red line. And you see that they actually join together at V around 70 something. And the anti-trap region continues to expand outwards, but then slowly tends to halt its expansion when it reaches more or less the size of the, well, the initial size of the black hole.
Yes.
Yes.
So you're saying that the anti-trap region is not transient, it's only permanent?
So that's a good question. So if you look at, there's a result in dilaton gravity in 2 dimensions that uses the same setup for the semi-classical parts of the 2-dimensional semi-classical terms. And in that case, in this paper, they find that the anti-trap region is also transient. So it expands and then shrinks. And we were expecting to find something similar here, but within the domain that we've been able to resolve numerically so far, it seems to stay at, so the outer surface tends to, in a time radius diagram, it expands outwards and then initially logarithmically, and then seems to hover around the size of the initial size of the black hole. Now, we try to push our evolution further, but we had some numerical issues evolving for very late times because there's some physical instabilities related to anti-trap region which lead to numerical instabilities. But what I would say is that even though this seems to be the result for these equations, if you add any perturbation to this anti-trap region, I would expect something to happen. I would expect some sort of instability. Say if you add a classical perturbation to it, I would expect that it turns again into a trap region, or it somehow, well, there is a white hole instability that is very similar to the inner horizon instability, and so that can be triggered just from classical perturbations. So I would expect that this object, which seems to become a remnant here, would be unstable under generic conditions, and that's also something that we want to study, and we're trying to study by improving our code. Yes.
Once the trap region has disappeared, is there still a region that appears with very high redshift with respect to observers that are far away, or what happens?
Well, once it finishes evaporating, what happens is that everything that, well, the expansion is more clear in the causal diagram. So what the outer region sees is anything that's in the future light cone of the evaporation point. But, well, what happens in practice is that, yes, there continues to be a high redshift region, which in this case is related to the presence of the anti-trap region. So you can see that the way, you can see this again from the way that the contour lines of constant are behaved here. Their behavior remains quite similar to the case of black hole horizon. And eventually, one would expect that if the anti-trapped region has disappeared, then let's say this contour line would end up joining this one, and then all of the redshift here that's accumulated would then relax and disappear. But within the part that we've been able to see numerically, yes, there's still a region of high redshift from the surface here.
And something I'm sorry I didn't understand in all of these plots. So the time scale that has been set, how does it correspond to actual physical time?
Well, it's in units of basically the horizon, so it's something like the light crossing time. So this so in this plot, if something advances to the middle, let's say vertically, that would mean something like square root of 120 gravitational timescales, or? Yeah. So, well, which one will be so?
Let's say to the point of the when the trap region disappears.
Yeah. Oh, from here to there,
Right.
Something like maybe 100 light crossing times because you're in the diagonal, something like that. So quite fast, but again we've put the plan scale to something quite large here. So another thing that I haven't included here is that because we haven't been able to resolve numerically the evolution much further than this, and also for plan scales that are much smaller than this, we are still not sure what the time scale of the full operation is. So it seems to become faster than the Hawking evaporation case. The Hawking evaporation scale goes with the cube of the mass. And in this case, the tendency that we've seen is that it initially begins in a very similar way for very large plan scales. And then if we continue analyzing it for smaller and smaller plan scales, then the tendency turns from cubic to quadratic, and then potentially from quadratic to linear. So it's something that we need to study further numerically to confirm, but potentially the evaporation time scale could become much faster with just Hawking evaporation.
Can I ask another question? I don't know if you'll get to this, but I'm just curious already. Was there ever an event horizon forming, if you consider the whole process? So from the time that you form the inner and the outer horizon, the time they disappear, was there ever an event horizon? Was there ever, because otherwise you're solving the information problem.
Yeah, well, for there to be an event horizon, you would need an outer horizon that appears and stays asymptotically. That's all. So in principle, no. But, well, we still don't know, for example, what happens to the anti-trap region. But yeah, it looks like there wouldn't be an event horizon. You would get. So in some evolutions, if we put some higher values of the Planck constant, what we find is that within the anti-trap region, something like a wormhole throw begins to open. So that's one possibility that happen at very late times. Here you have very high energy condition violations, so things like that can happen. So yeah, basically the future asymptotics are unknown, but probably no event horizon based on the fact that the trap region disappears. And when I say a wormhole throat begins to open, obviously you connect this, so the topology of the space-time won't really change. But it would be something like you would have a wormhole throat that then opens but then closes again toward the origin. Something like that. If you had a regular origin, in the case of a singularity. Well, even weirder stuff can happen potentially. We can't really say. Okay, so from here on, how much time do we have left?
Say 9-ish.
Okay, I'll go very quickly. So this is just to say what, so this is what's been done so far and published. From here on, we have ongoing projects which continue this in several directions. So one is exploring more general backgrounds within GR, but also in modified gravity theories. Also, I didn't mention that if we evolve only in a diamond that's in part of the space-time but doesn't connect to past no infinity, then we're making approximate in vacuum state. So the state that's let's say physical for the quantum field, we're approximating it in this region. But if we want the exact state, we would need to evolve all the way from past no infinity, and this can be done with a hyperboloidal foliation that goes between, say, the origin and past no infinity. This is another thing that we are working on. And also including classical perturbations, which induce mass inflation and would also induce potentially some instability of the anti-shock region that appears. And improving our numerical implementation, so getting a higher order conversion code and also with adaptive mesh refinement, because we have some problems of some very large radians that appear in some regions of evolution. And the final point is finding more accurate analytical approximations to the normalized stress energy tensor that would be applicable to a wider range of values of the parameters. So we have ongoing work for the first 4 points for finding more accurate approximations to the tensor. We have some ideas that also actually combine with the first point of looking at modified equations beyond GR. And I guess in the final minutes, I will very briefly go over what we're doing in those directions. So for more generic backgrounds, we started considering backgrounds which come from two-dimensional core density theories, and they can be considered the spherical reduction of four-dimensional or even higher-dimensional theories. But with this Lagrangian, we can basically get the most general second-order equations, which, well, in the absence of extra fields, which can represent the spherical sector of higher-dimensional spacetimes. And I'll stay too long on this. One thing we found in these spacetimes is that they generically possess regular black holes. Well, they can possess regular black holes as solutions, depending on the choice of the functions in the Lagrangian. And they can also, within those spacetimes, you can find exact analytical idea solutions. So, black hole formation solutions, which, and the fluxes that you can add can then also be used to, as part of the components that induce mass inflation. So, it's good that there will be some analytical control in these theories, more general backgrounds. As to the hyperboloidal foliation of the spacetime, as I mentioned earlier, it would basically be making a foliation that goes between the origin and past no infinity in order to evolve the in-vacuum states more precisely. And well, the reason we're doing all the calculations in no coordinates is because the normalized stress energy tensor has a particularly simple expression in the appropriate pair of no coordinates, but hyperboloidal coordinates can be constructed very simply from those no coordinates. If you're familiar with anything related to hyperboloidal foliations, it's the same people use to go to future no infinity and see, say, gravitational wave signals, quasi-normal modes, but going toward past infinity. And as for classical sources that induce mass inflation. We are implementing in our code now actually classical flux terms, both an ingoing one and an outgoing one. They cross within the trap region. We already have some promising results. And for the numerical implementation, I'll just mention that evolving in double no coordinates is a bit more tricky, and there's not been as many developments as typical space-time evolution codes, because you basically need to evolve in both directions simultaneously. Some functions evolve in one of the null directions, others in the other. And for our first results, we just use the second order method, RK2. And for that, you can do simply because you don't need the right method, you don't need midpoints between your grid points and the numerical evolutions. But for higher order convergent codes, you would need midpoints. And calculating the values of the functions at those midpoints becomes tricky if you need to evolve things in both directions. And we've made some progress in that. We found two ways of getting fourth order convergent codes, which haven't been seen in the literature so far. One involves a method which basically uses the midpoints and then calculates the functions to fourth order in the midpoints. So you need to use midpoints as the midpoints between the adjacent grid points. And another method which uses a mix of RK2 on the finer grid in the initial 4 iterations, and then an Adams-Bashforth method from the 4th iteration onwards, which also effectively achieves fourth order convergence. And on top of this, we're also implementing adaptive mesh refinement. And just to conclude, semi-classical gravity to deviations from classical evolutions, both the outer and inner horizons of black holes. The time scale of the inner horizon evolution is still unclear. We still need to perform further analysis. But it seems that generically an anti-shock region does form below the inner horizon. Its ultimate phase is still also part of our finding out as part of our future work. That's all. Thank you.
Thank you very much for the presentation. So we have a bit of time for more questions. Maybe let me already ask on Teams if there's someone online who has a question. Well, not for now, so yes.
That is someone who was
well, right now,
I have quite a few questions, but I'll
Okay.
have lunch with the others as well. I'll ask you. Well, I just ask one. I mean, maybe. So, first of all, very nice, and of course, the generality of these and validity of the assumptions are key. That's the formation of the anti-trap is very interesting. So, I guess I have two kind of short questions. The first one is related to the competition between the classical mass inflation and the evolution which is sourced by the renormalized energy mathematics. You seem to have said something like, because classical mass inflation will make the inner horizon go inward, whereas the quantum effect makes it outwards. They could compete, but you said in a very definitive way, if I recall correctly, that the quantum effect should dominate.
At lifetimes, it's expected that that's the case based on kinematical analysis. But yes, it's true that if you consider the full nonlinear evolution, then it's not entirely certain what will happen. I mean, by kinematical effects, I mean just involving classical perturbations and seeing the way the classical source evolves around the inner horizon when you approach the chief horizon compared to the scale of the semi-classical source. So the thing is that the classical source is generic perturbations which you expect to decay. The semi-classical source is suppressed by a Planck constant, but it doesn't decay. So just automatically you expect that at some point the semiclassical will start to dominate. And also just from the fact that one has a decrease, so has an evolutionary time which decreases, whereas the other one remains constant, can have an effect on the nonlinear evolution as well. So source that's constant can lead to a different nonlinear effect.
This model or this object will be constantly preaching this assumption that the classical source is decaying. Is it still valid?
Well, I mean, I would say that generically, if you consider astrophysical black holes, then you get long time intervals in which, okay, maybe you get some accretion which is in which that tendency is reversed, but overall with late times, let's say, there is also the cosmic microwave background radiation, which is also constantly being accreted. Also, you get things from the environment, but I would say that definitely at late times, and also we're interested in what happens at very early times. So, in a sense, just after the formation of the black hole. And so there you expect that, yes, you have initially some accretion rate from the matter that's around the black hole, but then that will also begin to decay. And I guess the effect that we're interested in is even before this perturbation goes below, as a source term, goes below the normalized stress energy tensor in scale, just from the fact that it decays in time compared to the constant, approximately constant flux term that you get from the normalized stress energy tensor around the inner horizon, just to see how the two, the back reaction from the two competes. And, well, I would say that will basically be what determines whether this problem can even be treated semi-classically or whether the curvature would grow and become Valentin in a time scale that's relatively short, which happens if mass inflation dominates, and then the problem will, one could say, goes beyond the semi-classical approximation. But of course, an argument can be made that from extrapolating from semi-classical gravity, you can attempt to get some effective field theory that you can use even when curvature becomes very large, just as a possible description, which, well, can be studied in the sense that it could lead to a consistent description that avoids singularities. So also a direction that's worth pursuing if it turns out that this problem can be treated strictly within the semi-classical regime. But either way, it's an open question still.
I'm satisfied. So
I think Hector has
This, well, I have a small question. So, when you add this effective energy momentum tensor from the semi-classical gravity, the addition of the two is the Einstein tensor. So this means that the addition of the two must be conserved, but in principle the two energy momentum tensors don't need to be considered separately. So in this model, it is considered that there is some interaction between the two. So the matter can lose or gain energy and momentum from the other.
So in this case, no, in this case they're conserved independently. And usually if you take, well, I mean, in this case we consider that the field that we're quantizing, which is the scalar field, and the electromagnetic field don't interact. So, yeah, each one, the stress energy tensor of each one be conserved independently. But you're right that in general, if you consider, let's say, the same field, and you have some part of it that becomes effectively classical because the energy scale is very large. But then you also consider in the part where it's the excitation of the field is very small, or it's in vacuum state, you consider a contribution from the normalized stress energy tensor of the field, then there could be an interaction between them. And also, just if one field is in a vacuum state, but it has some interaction with the other field, then yes, you could have a case in which they're not considered independent, but then you enter into the question of how do you model an interaction between a quantum field and classical matter, which is not really something that, well, there are some models, some attempts, but as far as I know, there's no consistent description of that. Interactions between classical and quantum systems, they tend to lead to some inconsistencies. So it's a complicated question, basically.
Any more questions? I have one actually. It's more about, well, maybe the numerics, but so you have this anti-trapped region. Usually when we do like the evolution of the exterior of black holes, we have the trapped region and we say, okay, we don't really care about boundary conditions there, everything's going inwards and nothing is supposed to go out. So how does it go here? Do you have to be careful with boundary conditions or with what's inside this region, say, that will go out?
So here from the start, we're evolving already everything that's inside the trap region and below the trap region. So in that sense, our boundary conditions are different. And particularly, we're evolving in a full diamond that with initial conditions on both null surfaces. And we're only looking at evolution that's fully determined by these initial conditions. And that encloses the entire trapped region and its evaporation potentially. So we don't have something like boundary at the horizon that we can ignore. We have, well, it's more similar to just evolving a patch of space-time in any other circumstances. Yeah, you evolve in the diamond where you have the initial data determines the evolution fully, and that's all.
Okay. Patrick, so regarding this anti-trapped region, is it, I don't know, like amplifying numerical noise, for instance, say that
yes,
everything would go out and...
Yeah, also when the horizons are still present, so we're finding that now when we're trying to add classical matter to induce classical mass inflation as well. The inner horizon also does that, because, well, the physical instability around it also leads to amplification of numerical noise, and the anti-trap region also has the same effect. So yeah, that's basically why we need to have mesh refinement in order to resolve some large gradients that form the boundaries, well, at the horizons and the boundary of the anti-trap region as well.
Okay, thank you. So you have a question? Okay.
I have a short question. So what is the relation between the strength of the singularity and the metric ring C0? I don't know if you said something about this.
Well, to be honest, I don't really know the details of how one translates into the other. I just know that if the singularity is such that it's weak in the sense that the deformation of objects is finite, then it also corresponds to a metric that's continuously extendable. I'm not entirely sure whether it's easy to see that intuitively or not. Yeah. I don't have an intuition for it.
Right. Yeah, because I remember that there was a paper which claimed to come up with an example of strong singularity, which was C0. So I don't know how important the assumption that this relation between C0 and the weak singularity is to the results.
Well, I think it just turns out, well, I guess whether you call singularity strong or weak is probably also something that might depend on which part of the literature you're looking at.
Yeah.
But yes, the mass inflation singularity turns out to be such that it's C0, so the metric is C0 extendable past it, and also that happens with the deformation of objects, that that's true. Well, there may be other cases in which the divergence of the scalars is slightly stronger, but the metric is still C0, so maybe that's a case in which you would call it a strong singularity, but still the metric is C0 standalone. I'm not really familiar. I mean, I only know about this because I was interested in mass inflation. I haven't really researched extendability of space singularity classification. So, but if you know, if you find out, let me know. I will be curious to know as well.
Okay, so I think we can stop here. Thank you again.